The type of solid is given by what types of forces hold it together. And so we have molecular solids, metallic solids, ionic solids, network covalent. The difference is in molecular solids, we have intermolecular forces. If the molecules are nonpolar, we'll have London or dispersion forces that hold them together. An example would be like a dry ice, CO2, or solid argon, helium, hydrogen. Normally these are gases. They have very weak forces. They aren't very sticky. In order for them to get stuck to one another, we have to cool down the temperature. And so we could even have methane, solid methane. And solid methane, it's going to be nonpolar. In fact, all hydrocarbons are nonpolar, regardless of the shape, but something that's tetrahedral like that, even if it were polar bonds, it would be a nonpolar molecule because all the bond dipoles would cancel in 3 dimensions. So if we have a methane molecule here, and we want that to get stuck to another methane molecule, we're going to have to really cool it down to quite low temperature. Because the only thing holding these together would be London forces or dispersion forces. And so that would be it. And so something like solid methane, we expect the properties to consist of something like this. They should be very soft, so you probably can easily crumble solid methane with your fingers. Extremely low to moderate melting points, depending on the molar mass. Now, not everything is like this. Solid methane will be like that, but we can have other stuff which is still soft, but it would be asphalt. Asphalt has a much higher melting point. In fact, to melt asphalt, you need quite high melting points. Quite high means you're going to need a flame or something to melt it. But asphalt consists of hydrocarbons, although the shape is going to be quite a bit different. It's a mixture. Asphalt's not pure. And these hydrocarbons are going to have long chains of carbon. And the long chains could be branched as well. And then we'll fill it out with hydrogens. So regardless of the shape, carbon-carbon bonds are nonpolar, carbon-hydrogen bonds are nonpolar. So hydrocarbons are nonpolar. So asphalt is a mixture of hydrocarbons, of big hydrocarbons. Big meaning, a lot of atoms. Since they're big, they're going to be heavy. But is that what keeps asphalt a solid, the weight of a molecule? If we think about an individual molecule, how much does a molecule weigh? A single molecule, even if it's very big, is not going to weigh very much. It's going to be much, much, much lighter than a piece of dust. And so there must be something else, because if you made the roads out of pieces of dust, are the pieces of dust really sticky to one another? A little bit, right? But if you blew on a pile of dust, what's going to happen? Are they sticky enough to hold together? No, it's going to disperse into the room and create an aerosol, or disperse into the air and create an aerosol. And dust particles themselves are going to be much, much heavier than a single molecule. And so why is it that when you blow on the asphalt on the street, it doesn't just blow into a dust cloud? And the reason is because they're pretty sticky molecules. They're pretty sticky molecules because of the London forces holding them together. And so the London forces may be extremely, we could have more complicated molecules too. But these are big molecules, a lot of electrons. They're more polarizable. These small molecules are going to be weak. So something like this, if you had solid methane, I wouldn't blow on it. If you blow on it, it'd probably just evaporate, or liquefy, melt, and then evaporate. And so the melting points can go to moderate melting points. Moderate, depending on molar mass. Actually, it's not because of molar mass. It's not because it's heavy. It's because larger molar masses have more what? Oh, more what? Yeah, more London forces. Why?
Because they have like more atoms to stick to.
More atoms to stick to, but really the instantaneous dipole, they have more electrons basically. And so some of these larger molecules have a lot more electrons and more polarizable, and therefore they're going to have larger London forces. We can also have polar, like this is dimethyl ether, this chloroform, HCl. Polar ones, these are still low to moderate melting points. Hydrogen bonding, it's still low to moderate. Hydrogen bonding being the strongest. But some of them are going to be quite strong, like molasses or syrup. It's very viscous and sticky. Water's less so, but water, ammonia. And so we have molecular solids that are held together by intermolecular forces. And the intermolecular forces are going to be dispersion, dipole, and H bonds, or a combination. So here's a combination, dispersion and dipole. Everything has dispersion because anything with electrons will. But generally speaking, these are low, melting, soft. Okay, then we go to metals. Let's take a look at metallic solids. Metallic solids are going to be held together with metallic bonds. So metals, we're going to have metallic bonds. In describing metallic bonds, we usually use the electron sea model. Electron sea model, where the ocean, the sea, consists of delocalized electrons. And so for metallic bonds, valence bond theory really doesn't work. What we do for metallic bonds is we do MO theory. And MO theory applied to metals is called band theory. And in fact, MO theory applied to any solid is called band theory. So we could apply this MO to all these, except for intermolecular. We aren't going to describe the bonding because there's no bonds. It's just an intermolecular attraction. And so let's take a look at something like gold, solid. And so if we take a gold atom here, and then we look at this, it turns out that each gold atom will be bonded to six other gold atoms in the plane. So this one gold atom is bonded to six more gold atoms in this layer. And then we're going to have a layer on top of this layer and a layer underneath. So if we look at the layer underneath, we can attach 3 gold atoms. These gold atoms are going to sit in these little pockets here, formed by the little void space, we call it, or hole between the atoms. So that's an additional 3. So this one gold atom has 6 plus 3. The 3 are on the bottom. And then we'll put 3 on the top. The 3 on top, I'm going to put it in an alternate hole. So this hole's what we call filled. So I'll put it in this empty hole here. And then this empty hole here. And this empty hole here. And so this single gold atom, how many other atoms is it bonded to? 12. So if I have 12, okay, 1, what is the shape of that? And 2, what is the hybridization? The shape we aren't going to do. What about the hybridization? The hybridization, 12. So 12 atoms requires 12 orbitals. 12 orbitals will be what? S, P, 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 that's 4, D, 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 it's 9. And then after I run out of d orbitals, where do I go? F, 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 F. sp3d5f3. Is that the hybridization of this? No, because we don't describe the bonding using valence bond theory and atomic orbitals. We describe the bonding here using molecular orbitals and something called band theory. Bands are bands of molecular orbitals. And so valence bond theory doesn't work for this. So we shouldn't apply it to this. Valence bond theory doesn't work for this, and it doesn't work for metal complexes. I talked a little bit about metal complexes yesterday, but I saw an interesting article yesterday on metal complexes. Let me bring that up. This was in C&E News. This is published May 18th in C&E News. But magnesium complex plucks fluorine from polytetrafluoroethylene, then gives it away. You know what PTFE is? PTFE is Teflon, like Teflon coated pans and that kind of stuff. And it's very tough, very unreactive, and so people think of it as a forever chemical, but they don't want them to be around forever. They're looking at ways to degrade it. And so this is one of them. They're using this magnesium complex, which we have the magnesiums bonded here. But when we do the magnesiums bonded in something like this, we don't use valence bond theory for this. You know, there's no hybridization, there's none of that. You know, we should use molecular orbital theory for this. So valence bond theory fails describing bonds in metals like that, and describing bonds in metal complexes like this. One of these PTFE type compounds has been banned in California. PTFE is Teflon and other fluoropolymers. But these are the PFAS. These are per and polyfluoroalkyl substances. These are used in fire suppressants and a bunch of other applications in creating rapid drying clothing, etc. And so people are looking at ways to destroy these types of compounds so they don't pollute the environment. So gold has a fairly high melting point, but some metals have low melting point. So for example, tungsten, that one popping up, has a high melting point as well. Sodium melts at a very low temperature. Sodium doesn't have the same exact structure as this. Sodium, this is what we call coordination number 12. In other words, it has 12 bonds. Each gold atom is bonded to 12 other gold atoms. It's coordination. Sodium metal has a coordination number of 6, so its structure is slightly different. Same thing with magnesium, some of these. Silver and copper are like gold. But here, the bonding is kind of weird in at least for the transition metals. If we look at the transition metals, the D block, and we look at the melting points, the highest melting points are kind of in the center of the D block here. So things like osmium, tungsten, ruthenium, these are manganese. These are very high melting points here. They peak in the center and go on. And on the edges, a little lower melting point. And it seems to be correlated with the number of unpaired electrons. The more unpaired electrons, the more bonding interaction there appears to be. The more bonding interaction, the higher the melting point. But the hardness varies from soft to very hard. So sodium you can easily cut with a butter knife. Silver would be more difficult. Melting point varies from low to very high. Sodium's pretty low. Tungsten's very high. They're lustrous in general. They're ductile and malleable. Ductile and malleable means this. The bonding is not two directional. So if I displace some of the atoms, it doesn't really break the bond. So let's say I move this move these three top atoms just slightly over. Will it still be in contact with that center? Yeah. It's just displaced slightly over. Or we keep moving it. And basically, with something like this, we can move or distort the structure a little bit and not break the bonds. And so this is called non-directional bonding. Whereas if we had, let's say, sp3 orbitals, that's very directional bonding. The orbitals should be in a 109-degree angle, and if I distort the angle too much, it screws up the bond. Here, it won't screw up the bond. So these are malleable and ductile. They're very good conductors of heat and electricity. The electrons are delocalized here. In MO theory, we say the electrons are delocalized in the conduction band. This conduction band is a set of molecular orbitals that span the entire solid structure. And it also gives it excellent thermal conductivity too. There's two ways of thermal conductivity. One are the electrons can transport kinetic energy, and the atoms can transport kinetic energy through vibration. All right, metallic, and then let's go to network covalent next. Network covalent has very directional bonding. Network covalent has covalent bonds. Covalent bonds we can derive using MO theory or valence bond. Sometimes it is more convenient to use valence bond. And so an example of this would be like diamond, carbon solid. Diamond consists of just sp3 carbon atoms. So we'll just use balls as the carbon atoms here and sticks as the bonds. And so we just got a bunch of sp3. And this is just going to extend out in 3 dimensions. It's a very ordered structure. But the situation with the diamond is diamond very malleable? Can you deform it and shape it into different shapes? No. Because if we tried to deform this, then that's going to screw up this bond. This valence bond theory is kind of nice for describing this. This would just be an sp3 sigma bond. And if we tried to move one of these carbon atoms, like distort it down here, that's going to screw up the overlap. The overlap should be head-on like this, but if the overlaps kink like this, we aren't going to get good overlap, and it's going to weaken the bond. End up fracturing the diamond. And so diamonds aren't malleable, they aren't ductile, because the bonding is very directional. Directional. The bonds are quite strong, though. And so diamonds have very high melting points. They're also very hard. Most are non-conductors. And so diamond's a classic example. Let's look at graphite next. Graphite consists of sp2 carbons. So rather than tetrahedral, we'll have trigonal planar. And they form these 6-membered rings. That just extend out. Into sheets of graphite. Diamond doesn't conduct electricity because electrons are localized. If I look at the valence electrons, they're localized in this sp3 sigma bond here. We have 4 of those. The sp2 electrons are localized here. We're going to have the sp2 sigma bonds. But we're also going to have pp pi bonds. And the pp pi bonds, well, on this sheet, all the p orbitals are perpendicular, so this is the top view. And overlapping. So it turns out that graphite is an excellent electrical conductor within the plane. And so the electrons can move freely in this extended pi bonding network here. And also heat, you know, electrons can transport kinetic energy as well. However, this is what we call an anisotropic conductor. Anisotropic conductor. An anisotropic conductor is it only conducts electricity in 2 dimensions. And so if we call this XY plane, it doesn't conduct in the Z. Because we have these sheets of graphite that are stacked one on top of each other. And there's no bond holding the sheets together. It's only dispersion forces. So let's take a look at diamond. This is diamond with the sp3 carbons. They just color-coded some of them, but they're all the same. This is graphite here. There are 3 sheets of graphite. Within the sheet, this is network covalent solid. All carbon-carbon sp2 sigma bonds and pp pi bonds. So double bonds. Or the actual double single. The actual bond order is 1 1/3. However, it's a little bit stronger than that because of the additional stability we get from what we call like the aromaticity of that. But anyway, here we have the sheets stacked one on top of each other. And if you look at the distance here, it's 335 picometers. The carbon-carbon with a bond order of about 1 1/3 is 142 picometers. So there's a big gap here. And that big gap is because the only thing holding the sheets together are dispersion forces. And so the dispersion forces aren't that strong, so it's easy to move the sheets on top of one another. And so it makes graphite, one of the properties of graphite is it makes it an excellent high pressure, high temperature lubricant. It's a good high temperature lubricant because it's got strong bonds within the sheets. It's a good high pressure because it's hard to crush. So network covalent solids in general are hard. So that's graphite. There are other forms of carbon too. There's a molecular form of carbon, the buckyball, C60, the Bucky tubes, or nanotubes. These are going to be held together by dispersion forces, and therefore we expect them to be quite soft. All right. That's network covalent solid. One more network covalent solid which we'll do will be a compound, not an element. And that will be quartz, SiO2. SiO2, quartz, is going to have a silicon in the center of a tetrahedron of oxygens. And so we have these SiO4 tetrahedra, and they just keep repeating. etc. Quartz is very hard. The bonding is very directional. It's going to be sp3 sigma bond. And they're strong bonds, so it's hard. It's high melting point. And what else? Non-conductor of electricity. The electrons are localized. They aren't delocalized. So they're localized in those sp3 sigma bonds. Okay, finally, we're going to talk about ionic solids. Ionic solids are going to be held together by ionic bonds. Ionic bonds can be weak, you know. So, for example, something like cesium iodide would be on the weaker end, whereas aluminum oxide will be on the stronger end. So cesium iodide would have a relatively low melting point compared to aluminum oxide, but still cesium iodide isn't so easy to melt. You know? So ionic bonds are fairly strong. So what we can say is moderate to very high melting points. Aluminum oxide has extremely high melting point. Cesium iodide you probably can crumble in your fingers. I mean, it's hard, but it's very brittle. Aluminum oxide is very hard and tough. You aren't going to be able to crumble it with your fingers. Cesium iodide is soluble in water. Aluminum oxide is insoluble in water. Aluminum oxide is the wonder of ceramic. I was working with a very high temperature oven, 1600 degrees Celsius, you know, over 2000 Fahrenheit, this oven. What's your home oven go up to? 500 Fahrenheit? Yeah, around there. So over 2000 Fahrenheit, in the high 2000s. And so what kind of stuff can you use glass in an oven like that? No, the glass, you see a pool of molten glass come back. It's way too hot. And so what did I use? I used these. They make a whole bunch of little cookware out of aluminum oxide. They call it alumina. Alumina is a wonder ceramic. So you could use this stuff. It doesn't melt. And it's very tough. Some of these aren't so tough. Like cesium iodide is not so tough. One of the reasons is because it's easy to cleave. What happens is this. If you try to displace this, let's say I'm going to deform this. I'm going to displace this layer of ions down. If I displace it down one position, then I'm going to have, rather than negative positive, which is interaction, I'm going to have negative with negative and positive with positive. So if I push this layer down and leave this layer in position, then it's going to turn into repulsion and it's going to fall apart. When they repel, that entire layer breaks off. This is called cleavage or cleaving. And so these are easy to cleave. I just have to displace it a little bit and then it breaks off easily. This one is not so easy because the bonds are so strong. It's really hard to cleave this. But anyway, they're hard, moderate to very high melting points, non-conductors, but good electrical conductors as liquid. Many are soluble in polar solvents, such as water. Yeah, up to a limit. All right, so those are the types of solids. Now what we're going to look at are the structure of these solids. We have two broad classifications for structures. We have the amorphous solids. Amorphous solids are like glasses versus crystalline solids. And so you can buy quartz in two different forms. You could buy quartz glass or you could buy quartz crystal. Quartz crystals have these beautiful crystals, but quartz glass just is like window glass. So amorphous, when we look at the building blocks, the building blocks of a crystalline solid consist of what we call unit cells. And the unit cell is the simplest repeating unit. And based on the unit cell, we can build up the entire crystal. It will just be a whole bunch of unit cells packed together. And so what we see is this: we can make a prediction. Let's say we're 300 angstroms out, or 300 picometers out. What unit cell do we predict, or what atom is going to be in that position? And so we have, what that is LRO. LRO stands for long range order. So long range order is, we can just predict at further and further distances what it should look like. Whereas in amorphous, there's slight distortions to these. And so in amorphous, maybe they aren't packed together as nicely. You know, and sometimes this packing requires time. So you gotta let like for example, water molecules, you gotta let the water molecules get in the perfect position to make an ice crystal. But if you don't give it enough time, you might get a frozen liquid. And so amorphous are often thought of as frozen liquids. There's a little bit of disorder there. Frozen liquids lack long-range order, LRO. And so it's hard to predict. If you're 300 picometers out, what do you expect it to look like? It's hard to predict. As far as crystalline solids go, we're going to look at, there are lots of different crystal structures. We're going to look at some of the simplest ones. In fact, we're going to look at the simplest crystal system. There are 14 systems. We're going to look at the cubic system. Cubic just means we're building this out of cubes. And these cubes are the simplest repeating unit. And so the first cubic one we're going to do is what we call primitive or simple. And if we take a cube and then just put 4 atoms on the corners, on the top, and 4 atoms on the corners on the bottom, this is basically it. And so we're going to build that one now. This is a participation lab. So you aren't going to have to turn in a report for this, but you should build these structures. So did everybody get a model kit? Go ahead and get one. So they said they called it the methyl ether of benzoic acid. Benzoic acid has a benzene ring, like graphite. This. Usually for benzene rings, we draw the hybrid thing. This. Or we could draw one of the resonance forms, like this. Alternating double bonds. And then we have a carboxylic acid group here. But rather than being a carboxylic acid, the carboxylic acid group has a hydrogen here. And rather than a hydrogen here, we have a methyl group here. And so this is why it's called methyl benzoate. Because it's like benzoate, but it has a methyl attached there. This is called an ester. And then we have hydroxide. Where do you think the hydroxide will attack?
So probably the carbon that has the 2 oxygens on it.
Yeah, probably at this carbon. I'd say that's the most probable site for attack. Why?
Because it has the highest positive dipole.
Yeah, it has the highest positive charge. And so, because it's got these two oxygens. Actually, the oxidation, we could do it by oxidation state too, but this is going to be quite positive. It's delta plus 1. And 2, if these electrons come in here, we're going to have too many bonds. But we can kick some out. Which ones can we kick out? We can kick out the pi bonding electrons, can we? And then it can attach here. Alternatively, we could have attacked this carbon here, but if we can attack this carbon, then we can't just kick out pi. We're going to have to, something's got to leave. And so if we attack this carbon here, then maybe this has got to leave, or hydride has got to leave. Does that make sense? And so this seems a lot more likely, doesn't it? Well, let's continue on here. Here's the mechanism.
Into the shape of water molecule.
Arch, this is good evidence.
is X-ray? X-rays are hot. The energy is light with a repeating period called the wavelength. Since the wavelength of an X-ray is similar to the distance between atoms in a crystal, a special interference effect called diffraction can be used to measure the distance between the atoms. Interference occurs when X-rays interact with each other. If the waves are in alignment, the signal is amplified. This is called constructive interference. If the waves are out of alignment, the signal is destroyed. This is called destructive interference. When an X-ray encounters an atom, its energy is absorbed by the electrons. The electrons occupy special energy states around an atom. Since this is not enough energy for the electron to be released, the energy must be re-emitted in the form of a new X-ray, the same energy as the original. This process is called elastic scattering. In a crystal, the repeating arrangement of atoms form distinct planes separated by well-defined distances. When the atomic planes are exposed to an X-ray beam, X-rays are scattered by regularly spaced atoms. Strong amplification of the emitted signal occurs at very specific angles, where the scattered waves constructively interfere. This is called diffraction. The angle between the incident and the scattered wave is called 2 theta. In order for constructive interference to occur, the scattered waves must be in alignment, meaning that the second wave must travel a whole number of wavelengths. In this case, 1/2 of the wavelength is traveled on the incident side, and 1/2 on the scattered side, revealing 1 additional wavelength. In the case of the next X-ray, 1 wavelength is traveled on both the incident and the scattered side, resulting in 2 wavelengths. This reinforcement occurs throughout the crystal.
All right, are we ready? Okay, the first crystal we're going to just build the simplest unit. And the simplest unit is called a unit cell. And here are 3 unit cells that we're going to build. The one on the left is a simple or primitive unit cell. It's a little bit more than the unit cell. In order to build this, we're going to need the handout here. We'll go to page 9. Go to page 9 and we're going to build the primitive cubic unit cell. We have 2 bases. We have the half circle or half moon, and then we have the full moon base. So I'm going to take the half moon base and then find paper template A. And then line that up with the base. In paper template 8, you have a shaded square. You're going to put a metal rod in each corner of the shaded square. Okay, then you're going to put a colorless ball on each rod, and that's going to be layer 1. The next layer is called 1 prime, and layer 1 prime is layer 2, it's just a repeat of layer 1. So you end up with this. If you have, let's say, gold atoms, or if you have oranges, is this the most efficient way to pack them? Like one directly on top of the other? It turns out it's not. In fact, if you look in the center of this, do you see that huge hole in the center? It's called a cubic hole, because if you're in the middle of this hole, you're in the middle of the cube. Do you see? And so that's called a cubic hole. That's a lot of empty space. Certain atoms can fit in that cubic hole. Like, try to fit a colorless one, try to just jam it into the middle, into the cubic hole. Does it fit so nicely? No. Expands out. You know, an atom that would fit nicely is the green one. Get the green one and jam it into the cubic hole, and then it's got a perfect fit. Do you see that? Okay. So, if we put a green one in there, do you know what crystal we just generated? This one's called cesium chloride. And so if we put the cesium in the middle and chlorides on the corners, that's the cesium chloride crystal. If we take that one out, do you know what crystal we just generated? This is polonium. Polonium is the radioactive metal used as a poison. So in body center cubic, the corner atoms are pushed out, so they no longer touch. And so I'm going to just draw the corner atoms here. Okay, then what I'm going to do is I'm going to draw a triangle. I'm going to use this edge here. This is called a face diagonal. So I'll draw a face diagonal. Do the atoms touch along the face diagonal? No. And then what I'm going to do is I'm going to go from this corner here on the top left in the back and go to this corner here on the bottom right front. That's the body diagonal. And this body diagonal is going to cut right through the center. There's an atom right stuck in the center of this cube, which I didn't draw here. There's an atom stuck in the center. So we're looking at where the atoms touch. And so I'm going to just draw this triangle out here. Like that. This is A. This is the face diagonal here. What is the length of the face diagonal? We can figure out the length of the face diagonal because one side of the triangle here is A, and this is also A. So it's an equilateral triangle. What is the hypotenuse of an equilateral triangle if the length is A? So we have an equilateral triangle that's going to look like this. A, and then we have the face diagonal here. What is the length of the face diagonal here?
Just A squared. 2A.
Close. Close. It's square root of 2A. We use Pythagorean theorem or just memorize it. Square root of 2A. It's the length. What is the length of the body diagonal here?
Square root of 2A plus A.
Okay, the length of the body diagonal is easy to memorize if you don't want to do the formula. It's square root of 3A. And the body diagonal is where the atoms touch. And so I have an atom stuck right in the center here. And then half an atom here on the corner. These should be touching here. Half an atom here on the corner, and another half an atom on the corner here. And so how many radii do I have? I have 1, 2, 3, 4. 4 radii that touch along the body diagonal. And so 4 radii is equivalent to square root of 3A. We're going to need that in a minute. But before we do that, let's do the same thing. What is the coordination number here? Take a look at that center atom. How many atoms is that center atom touching? 8. And so the coordination number is higher. It's 8. The corner atoms are the same. The corner atoms are going to be coordinated to 8 others if we build the cube out. How many atoms are contained inside the cube? So I have 8 corner atoms. Only 1/8 of a corner is inside there, so that's 1 atom. And then I have 1 internal atom. And so that's going to give us a total of 2. That's correct. There are 2 atoms per cell. And so the coordination number is 8, and there are 2 atoms per cell. That's from 8 corners times 1/8 of a corner per cell plus 1 internal, and that whole thing's in the cell. So we could say times 1 internal per cell. Do you think the packing efficiency is higher? Well, let's calculate the packing efficiency. Can you calculate the packing efficiency? How many atoms are in the cell?
2.
So 2 times, and each atom is going to have a volume of 4/3 pi r cubed, divided by the cell volume, which is A cubed. And so this is why we had to do the triangles. We had to do the triangles to come up with a relationship between A and R. Since the atoms didn't touch along the edge, it made life more difficult. Actually, this is the most difficult one to calculate. Let me know when somebody gets the packing efficiency. Does the packing efficiency look greater than, less than, or about the same?
I think it's less efficient.
Less efficient than primitive? Okay. Yeah, the gap is a little bit smaller. In fact, let's take a look at the gap in more detail. So what I'm going to do here is we're going to put in one more rod. So do you see layer 2? I'm going to put one more rod so I can put one more atom for layer 2 on the side of this. And so now I just have a atom stuck on the middle of the face. Do you see that? Okay, now that hole, look at the hole that's encapsulated by those atoms. The previous hole is called a cubic hole, and it's quite big. This new hole is not called cubic, and it's a lot smaller. What do you call that hole? So if you look at, okay, let's try to put an atom inside that hole. So what I'm going to do is I'm going to lift this up and then just try to put it, the green one's too big. Do you see the green one's not going to fit inside that hole very well? And so what I'm going to do is I'm going to try to take a blue one. You can get a blue one out of the little container and then try to put a blue one there. A blue one is a little bit too big. Do you see the blue one doesn't really fit in that hole without distorting the structure significantly? Okay, we only have one other size left, and that's the pink one. Pink one is a little bit too small, and it's going to fall out of that hole. Do you see that? And so the size of the hole is between blue and pink, but it's definitely smaller than green. And this hole, when you look at it, how many atoms surround that hole? Count them. Six is correct. There are 6 atoms coordinating that hole. So do you know what we call this hole? What's that geometry, Vesper geometry, where you have 6 atoms attached to the center atom called? No, that's 5. Be the next one after trigonal bipyramidal. What's after trigonal bipyramidal? Octahedral. This is called an octahedral hole. So the biggest hole we had was the cubic hole, and now we have a smaller hole, the octahedral hole. We have more of them, but they're smaller. And so it turns out that this is a little greater packing efficiency. Okay, let's calculate the theoretical density. So what adopts a body-centered cubic structure? Let's take a look. Iron, sodium, potassium, tungsten. Which one do you want to do? Sodium? Okay, why don't you calculate the theoretical density of sodium? So sodium weighs, an atom of sodium weighs 23.00 U. This is sodium metal, not sodium ion. And so what is the radius? Of sodium metal, of the sodium atom. Let's see. going to look up the metallic radius of sodium. Well, we'll just use this 227, sorry. $227. Picometers. Why, the radii are all over the place. Shoot. I'm not getting good data here. I'm getting numbers all over. Let's use the book. Okay, 186. We're going to use the metallic radius. 186. So theoretical density of sodium 0.964 versus experimental here 0.968. It's close. It has the highest packing efficiency for an element. In fact, gold has this packing efficiency here. But let's take a look at the holes here. Do you see in the center of this is empty? Is there anything in the center of the cube? No. What kind of hole is that in the center of the cube? And so I'm going to lift the center top atom off, and then I'm going to get a blue one. And I think the blue one will fit nicely there. So I'll put the blue one on the center rod. Let that drop. And so in the center of this cube, I have one blue. Can you see that? And then I'll put the one on top again. And then I'll look and see that blue one's bonded to how many other atoms? 6. And so do you know what kind of hole that is? Cubic is 8. 6 is think SF6. When 6 bonded atoms, it's going to be called, starts with an O. octahedral. And so right in the center of this cube is an octahedral hole. But if you look at the middle of the edge of the cube, there's another hole. So get another blue one and stick it on the side rod. Right in the gap. Do you see that gap at the top? Now, if we were to surround this blue one, how many more colorless ones could we fit around that? Yeah, a total of 6. 2 more. So do you know what that's called? Octahedral hole. So we have an octahedral hole in the center and then an octahedral hole in the middle of each edge. Do you see that? And the blue ones fit nicely there. If I put blue ones on each of the octahedral holes, do you know what structure I just built? It's sodium chloride. Where the sodiums would be the blue ones and the colorless ones would be the chloride. All right, let's get rid of the blue ones. If I get rid of the blue ones, I'm going to get rid of the blue ones and then take a corner atom and lift it up. If you take a corner atom and lift it up, it sits in a pocket of 3 atoms. Do you see that? Okay, then what you're going to do is you're going to get a pink one. And the pink one you're going to drop right in the center of those 3 atoms in which the corner touches. Like that. And so I have a pink one centered where I lifted a corner off and then I put a pink one there. Oops. And then drop the corner back down to trap the pink one. So in other words, pull a corner, hold it like this so the corners, hold the 2 opposing corners like this so it's vertical, it forms a vertical axis. And then lift this corner one off here and then drop this pink one in the little space. And so do you see there's a pink one trapped underneath the corner? How many atoms is that pink one bonded to? No. Try it again. Here, if you want to come take a look, I have it here. There's a triangle of atoms, 6 atoms. And the pink one's in the center of that triangle of 6 atoms, if I lift the corner one off. So I just pulled the corner one off. Here's the corner one. I lift it off and then put a pink one centered in those 3. Four. 4 is correct. And do you know what we call it? Tetrahedral hole. Will a blue one fit there? No, it's too small. And so the biggest hole is a what? The biggest hole is a, not octahedral, cubic. Then the next biggest would be octahedral, and the smallest hole will be tetrahedral. So if you look at how many tetrahedral holes are there? Well, there's one underneath each corner atom, and so there are 8. If you fill half of those, then I built zinc sulfide, where the pink ones are zinc and the colored ones are sulfide, if I fill half of them. All right, What's that?
I want you to label them. How do you layer them again?
3 layers. Layer 1 is going to have, just look at where there's 1. It's going to have 1 in the middle and 4 on the corners. Layer 2 has balls in the middle of the square. What's that?
So is it 2 in the middle after the second layer, right?
And then layer 3 is the same as layer 1. Did you get it? Okay, so again, to repeat, in the middle of this cube is an octahedral hole. And there are octahedral holes in the center of each edge. Underneath the corner is a tetrahedral hole. Did you get it, Isabella? You should get a structure that looks like this. All right, the next thing we're going to do is this. We're going to look at face-centered cubic is also called cubic closest packing, and gold packs this way. And the way we can tell is this. Grab 2 corners, opposite, opposing corners along the body diagonal. And tilt this so it stands vertically there. Do you see 4 layers? Okay, look at layer 1. We call that A. Layer 2 is B. Layer 3 is C, and then we go back to A. And so this is an A, B, C stacking of closest packed layers. And so what you're going to do is you can remove the top 2 layers by just sliding them over. And then look at the layer that you just exposed. Do you see the layer that you just exposed is a closest packed layer? And the layer that you just pushed off is a closest packed layer. So this is called cubic closest packing. Can you see the closest packing in the layers? Minimal gaps. And so this is ABC. Cubic closest packing. This is a repeating pattern. Layer A, B, C, A, B, C. The other type of packing we have is called hexagonal closest packing. It has this exact same packing efficiency, but it's an AB pattern. And so the third layer is superimposed with the first layer, but we aren't going to build that here. We're just going to look at this. So what we want to do is we want to determine the packing efficiency. This is called face-centered cubic or cubic closest packing. And then we're going to calculate the theoretical density. So let's go ahead and do that. So in face-centered cubic, there's no atom in the center of the cube, but the corner atoms no longer touch. The reason the corner atoms no longer touch is because, why? Corner atoms don't touch in face-centered cubic because they're spread apart by the
layer above.
face-centered atom here. And so the atoms touch along a face diagonal. So take a look at the face and we see the atoms touch along that face diagonal. The face diagonal is going to be defined like this. This will be our face diagonal here. That's where the atoms touch. How many radii is that? It's 1, 2, 3, 4. What is the length of this? The length of this, well, this is A. This is A. And so the length of this, the face diagonal, we already figured out earlier, it's square root of 2 times A. And so we get the relationship here. Square root of 2 times A is equal to 4R. So why don't you calculate the packing efficiency? How many atoms in the unit cell and what is the coordination number? So first let's look at the coordination number. Let's pick the atom in the center of the face. Do you see the atom in the center of the face is coordinated to 4 corners? And then look behind it. How many of those other atoms are coordinated to that? 4. And then on top of this, they're going to be 4. And so it's 4 times plus 4 is 12. So the coordination number is 12. How many atoms are there in a unit cell? Okay, there's a total of 1 atom from the corners. And then each face atom is sliced in half. And we have 6 faces. So 6 faces, and each is sliced in half is going to mean 3 atoms. And so there's going to be a total of 4 atoms per cell. So the coordination number is 12, and there are 4 atoms per cell. And that's going to come from 8 corners times 1/8 plus 6 face atoms times 1/2 atom per cell. Okay, the packing efficiency is if we have 4 atoms, that's the occupied space is going to be occupied by 4 atoms worth of volume. So that's 4 times 4/3 pi r cubed divided by the volume of the cell, which is A cubed. And then we need the relationship between R and A, which is given here. And then we can figure out the packing efficiency. So why don't you go ahead and calculate the packing efficiency for this? Times 100%. Does somebody have it? 70 what? 74.05. So 74.05% is the highest packing efficiency. There's only 25% void. And the 25% void is going to be taken up by the octahedral and the tetrahedral holes here. There's one more hole. This is a trigonal hole. Okay, let's calculate the theoretical density. What do you want to calculate the theoretical density of? Let's calculate the theoretical density of gold. The mass of gold is 196.97 U. 196.97 U. And the radius, let's look at the metallic radius for gold. Hopefully it's readily available. Okay, I guess we'll just go with this one, 144. Metallic, we'll just assume that's the metallic radius. 144 picometers. Actually, we can measure what A is using X-ray diffraction. And then we can determine the radius based on A. So it gives us an easy way of measuring A. In this case, we're trying to figure out what the density is by knowing what the radius is. And so radius will do 144 picometers. And we'll try to get the yeah, a little under 20. What are you getting?
What low would be? I got
13.69 is quite low. Anybody else? All right, we're running short on time, so you can work on that calculation later. What you're going to do is get rid of the top two layers of the face-centered cubic. Leave the bottom layer. And then flip to page 33. Do you see 0 underscore 7.4 D? That's a plastic spacer. So you need 4 spacers about that length. Do you have them? Look in the plastic Ziploc bag and see if you have plastic spacers of that length. If you don't, cut some. We have some scissors in a bucket next to Isabella there. You can cut some spacers, and then what you're going to do is you're going to put the spacers on the 4 side rods. Yeah, all the way to the bottom. That's our layer 0. So it's the same as before, except now we have spacers. Okay, did everyone get that? Okay, do you have spacers? The same length as on the paper. So just match it to the paper. It's a scale. And then put it on the 4 empty rods. Okay, then what you're going to do is you're going to put a blue one on top of each spacer. And so you need 4 blue ones to put on the 4 plastic spacers. And then we've completed layer 1. This is layer 1 of sodium chloride. And we just fit in the sodiums into the octahedral holes here. Okay, now we're going to build layer 2. Layer 2 is put 4 corner blues and 1 center blue. So 4 corner blues and 1 center blue. Each blue one should reside on top of a clear, colorless ball. All right, and then we're going to put 4 colorless ones on the side of the square. And that should complete layer 2. Okay, layer 3 is going to be a repeat of layer 1. And so layer 1 had 4 blue ones on the side. And then 5 colorless ones on the corners and the center. And so what we have here is we have a face-centered cubic lattice of chlorides, and the sodiums occupy all the octahedral holes. So you should get something like this. All right, now what we're going to do is we're going to try to figure out how many atoms there are in the unit cell. So we already figured out for the colorless ones, they're going to be, how many were there? 4. How about the blue ones? How many blue ones are inside the cube? Okay, the sodium chloride lattice. I'm going to calculate the things over here.